In Module 8, Section 3, we will learn how to solve word problems using systems of equations. Remember the problem-solving process. We begin by understanding the problem. We may read and reread the problem. We always want to choose two variables to represent the two unknowns, and sometimes that's the best place to start. And then if it's necessary, or if you feel more comfortable doing so, construct a drawing or a diagram of some sort. Then we translate the problem into two equations. We solve the system of equations that results from that, and then interpret the results. Make sure that your answers make sense. Let's get right into an example. One number is 4 more than twice the second number. Their total is 25. Find the numbers. And so we start with the last sentence, find the numbers. That's how we're going to define the variables. X will equal our first number, so we'll say x equals a number, y equals a number. Now that we know what we're trying to find at the end, let's go back through our equations and determine what mathematical operator terms we have and what important words we see. So we start with one number. Remember that stands for, we'll just call it x, is more than, twice is another mathematical term. The second number, we'll call this y. The total is, now if we go back through again and look at the important numbers, we have 25, 4, and that looks like we've used most of the information. So let's start just by directly translating. One number, x, is, remember is means equals, 4 more than, 4 plus, twice, so we're going to multiply something by 2, twice the second number, so 2 times y, or just 2y. We're also told that their total is 25. Total means addition, it means the sum. So x plus y, the total, is 25. And at this point, we have two equations with two unknowns, and we can solve either using the substitution method or the addition method. Because the first equation is already solved for x, let's take its expression and plug it in for x in the second equation. So this is the substitution method that we're going to try to use. The second equation becomes 4 plus 2y plus y, so 4 plus 2y takes the place of x, plus y equals 25. We combine like terms on the left-hand side, and we get 4 plus 3y equals 25. We then subtract 4 from each side. We have 3y equals 21. Now we divide both sides by 3. We're left with y equals 7. So we found one of the numbers. We take 7 and plug it back into the first or second equation. It doesn't matter. That will give us the second number. Let's plug it into the first equation. X equals 4 plus 2 times y. In this case, y is 7. So x equals 4 plus 2 times 7 is 14. And 4 plus 14 is 18. So we have x equals 18, y equals 7, and we've solved the word problem. Let's try another example. Hilton University Drama Club sold 311 tickets for a play. Student tickets cost 50 cents each. Non-student tickets cost $1.50. If the total receipts were $385.50, find how many tickets of each type were sold. Again, if we start at the end of the problem, we want how many tickets of each type. And so right away we might say x equals student tickets and y equals non-student tickets, because those are the two types of tickets that were talked about in the word problem. So let's go through and again circle any mathematical operators, box any numbers that we think are going to be important at the end. So we're told that they sold 311 tickets total. That's important. They tell us that student tickets, remember student tickets, that stands for X. They cost 50 cents each. So they cost 50 cents each. Non-student tickets, that's our Y variable, cost $1.50. The total receipts were $385.50. So let's start with that last piece of information, the total receipts. Remember, total on the last problem at sum, total receipts here also means sum. We're going to have the cost of student, so cost of X times the number of tickets of X that they sold, plus the cost of Y times the number of Y tickets that they sold, will equal $385 times 50 and 50 cents. So if we plug in the information from the problem, we're told that student tickets cost 50 cents each, so 50 cents times X, plus we're told that non-student tickets are $1.50, so $1.50 times Y equals $385.50. So now we have one equation. The next piece of information that we're going to use, we were told that the drama club sold 311 tickets altogether. So if we add all of the student tickets and all of the non-student tickets, that should add up to 311. So now we have two equations with two unknowns. One takes care of the cost of each ticket and the total amount of money earned. The next equation takes care of the total tickets that were sold. So we can take the second equation and solve for either variable. If we solve for y, we'll be left with y equals 311 minus x. And on the next slide, we're going to plug that into the y value for the first equation. So our second equation was y equals 311 minus x. Our first equation was 50 cents times x plus $1.50 times y equals $385.50. So if we plug 311 minus x into the y variable in the second equation, this is what it looks like. 0.50x plus 1.50 times 311 minus x equals $385.50. Now at this point, we need to distribute the $1.50 to both pieces inside parentheses. When we do that, we get 0.50x plus 466.5 minus 1.50x equals 385.50. On the left-hand side, we combine like terms. So we get negative 1x plus 466.5 equals 385.50. We now subtract 466.5 from both sides of the equation. They cancel. On the left-hand side, let's come up to the top where we have more room. And we're left with negative 1x equals, on the right-hand side, we have to subtract those two numbers. And it turns out that will give us negative 81. So we divide both sides by negative 1, and we're left with x equals 81. Now at this point, it's important to go back to that original label. Remember, X stood for the student tickets. So they sold 81 student tickets. Once we have a value for X, we can plug it into either equation. I'm going to plug it into the equation that's solved for Y and doesn't contain any decimals. So we have y equals 311 minus 81, and that means y equals 230. And remember, y stands for the non-student tickets. Here's another example, and in this example, we're going to use the equation distance equals rate times time. Terry Watkins can row about 10.6 kilometers in 1 hour downstream and 6.8 kilometers upstream in 1 hour. Find how fast he can row in still water and the speed of the current. So we have two variables we're trying to find. We want to know how fast he can row in still water. Also, we want to know the speed of the current. So we can call the first x and the second y. It's important to note that the speed going downstream and upstream is going to be different. So if I'm going downstream, we'll take whatever the boat's speed is, but we will also add the speed of the current. So that would be x plus y for my speed. However, if we go upstream, then we're fighting against the current of the river. So we take the speed of the boat, but we have to subtract the speed of the river because that will actually slow us down in this case. So let's try to create an equation, one for the downstream information, one for the upstream information, using the pieces given in the original word problem. So we're told that Terry can row 10.6 kilometers in 1 hour downstream. Let's use that information and come up with the downstream equation. Remember, distance equals rate times time, so the distance is 10.6 kilometers, and that equals the rate we already found out on the left side of the screen is x plus y, the speed of the boat plus the speed of the river, because it's helping as we go downstream, times time, which in this case is 1 hour. Now for the upstream information, it says he can row 6.8 kilometers upstream in 1 hour. So our distance is 6.8. Our rate we've already found, x minus y, and our time is still 1 hour. So we simplify, we multiply the right-hand sides by 1. Anytime you multiply by 1, the other factor doesn't change. So we have 10.6 equals x plus y, and we have 6.8 equals x minus y. Now you may notice that your y variables are already opposites, so at this point it would be okay to add our equations together. Take that value 8.7 and plug it into either of the original equations. I'm going to plug it in to the first equation, and that will give us 10.6 equals 8.7 plus y. So we subtract 8.7 from each side, and we're left with y equals 1.9. Let's try one more problem. A Candy Barrel shop manager mixes M&Ms worth $2 per pound with trail mix worth $1.50 per pound. How many pounds of each should she use to get 50 pounds of a party mix worth $1.80 per pound? Now you're going to see a lot of problems like this in the homework. Sometimes we use candy that's worth a different amount per pound. Sometimes it's a solution of an acid that has so much percent acid in the solution. But every time it's going to be like this. Basically, you will take your quantity of your first plus your quantity of your second, and that should equal your total quantity. Every time for this type of problem, that will be your first equation. Your second equation will be the rate of the first quantity times the amount, so rate times quantity, plus the second quantity will be multiplied by its rate as well. We'll talk about what the rates are in just a minute. So rate times quantity. And on the right-hand side, we will have the final rate times the total quantity. Now, when we say rate, it's either going to be, for these problems, a percent or a cost. So if you go back and you look at the information we have for this problem, you're going to see it's a cost. It's that cost per pound. Sometimes it will be the solution or something of that nature. And plug in the information from the problem. Let's see what kind of equations we get. Our first quantity, we have M&Ms. Plugging it into our first equation, the top equation we wrote, we have X M&Ms plus trail mix, we'll call that Y. So Y trail mix equals, at the end, we want to get 50 pounds. So many pounds of M&Ms plus so many pounds of trail mix equals 50 pounds. That's one equation. The second equation, we're going to multiply our variables times their worth, because that's the rate that was given, the cost per pound. For instance, M&Ms, $2 per pound, so we'll multiply that by 2. Trail mix was worth $1.50 per pound, we'll multiply that by $1.50. And the 50 pounds at the end, we want it to be worth $1.80 per pound. So plugging that information in will give us 2x plus 1.5y equals 1.8 times 50. Now the only bit of cleaning up I'm going to do right this minute is multiplying the 1.8 times 50, and we'll do the rest of it on the next page. So when we take 50 times 1.8, that gives us 90. Let's use these two equations on the next page to solve for the pounds we want of each candy. So we had x plus y equals 50, and 2x plus 1.5y equals 90. Now, since we've used the substitution method for one problem, addition method for one problem, hopefully you're comfortable using either one. Here we might decide to use the addition method. So I'm going to multiply the top equation by -2. And we'll do that so that our x's will become opposite. So we have -2x minus 2y equals -100. The second equation won't change at all. When we add our components together, the x's cancel. We're left with -0.5y equals -10. So we divide both sides by -0.5. And we determine that y equals 20. Well, we can plug that value into the original first equation. X plus 20 equals 50. When we subtract 20 from each side, we find out that x equals 30. So in order to get the desired mixture, we will use 30 pounds of M&Ms and 20 pounds of trail mix. Not every problem in this section will look exactly like the examples, but use the information from the problem to find your unknown quantities and do the best you can once you set up your equations.